So got a question. How many of you have heard of 12-factor apps? Okay. Was it just, how many of you heard of 12-factor apps before you discovered I was going to talk about 12-factor apps? Okay. And how many of you are using 12-factor app methodology? Okay, let's see. Okay. All right, ask some other questions as we go along, but that's a good starting point. This is me. Most of that is very dull, just as I'm old. You can tell by the beard, though. When I was pointing out, just to reiterate what was said earlier, right? I started speaking in 2003 in .NET because I was a C++ dev, and .NET came out, and we were all very excited by .NET because, frankly, getting anything done in C++ was hard because it took a long time. There's a lot of code to write. And so I was running a user group because I thought, let's all get together and talk about .NET, this new exciting thing. And I ended up running a user group because all the Americans had user groups. And I said, where is the London .NET user group? And someone said, there isn't one, but I'll turn up if you start one. So I got in touch with some American guys, and they said, okay, you know, Develop Mentors, they were called, like an old training company. They gave us a venue. And then we quickly discovered we didn't have enough people to speak. We couldn't find enough Microsoft employees to fly in to kind of talk. So we had to do talks ourselves, right? And that kind of started me on this path. And you start off by doing small 15-minute, like what we call lightning talks, and then you get to bigger talks. And one of the problems with speaking at an event like this, I tend to find, is that you are the content, right? You know your stuff about technology. The slide deck's there to help you navigate through. The biggest thing you need is confidence, and unfortunately, the easiest way to get confidence is simply to speak enough times in front of people that it doesn't intimidate you anymore. But I would really recommend doing it. I have been very fortunate to, go to lots of places, speak to different conferences, travel around, meet a lot of people who I would probably otherwise have just sat in London and never met anybody, right? And so I would really encourage you to speak if you can. Okay, that's who I work for. We're kind of a SharePoint alternative. We tend to work between organizations. The main point of showing you this slide is not to try and sell you Huddle. It's just to say I don't work for some kind of consultancy. I am not selling you my particular anything at all. I'm just trying to give you the benefit of my experience and how we work. All right. So what we'll talk about first of all, we'll talk about the context. So we'll talk about why 12-factor apps have become more important as an idea. Those of you that said, I've heard of it, you've noticed sort of in the last 12 months or so, there's been more of a kind of like, oh, this is 12-factor apps thing, right? Quite often mentioned in the same breath as cloud native. Who's heard of cloud native? Yeah, okay, we'll talk about cloud native as well. Okay. Where did it come from, right? Its origins? What are its goals? Why would you care about 12-factor apps as an idea, right? Why listen to the whole of the talk? Why not go home after pizza? Okay. 12 factors, what are they? So what I used to do this talk, I send people, and I would do all the 12 factors one by one, right, when I first started. And it turns out when you're giving like a conference and you've got like an hour, that gives you 5 minutes per factor. It doesn't really work very well. So now what I tend to do is really divide them up into 3 big groups: design, build, and release, and manage. There's a pit trap there. Design, build, and release, and manage. And I talk about them holistically within those 3 buckets. And then at the end, we'll kind of review exactly what the factors are. And we'll show some code throughout all this part of the talk. Right, so I actually show you some apps built in that style. Okay. That's less relevant here than at a conference. So that if you are at the back, if you have trouble reading or hearing me, just shout from the back and say, too soft, or I can't see, too small. Because what happens occasionally is I get feedback forms and the person in the back says, I couldn't see or I couldn't hear Ian. And it's kind of like, well, say something. Okay, so at the back, I can fix any problem. All right. Well, I do offer to here that you can go on GitHub and get most of my presentations. Don't sync the, unless you've got a lot of bandwidth, don't sync the presentation directories. Grab the ones you want directly. And the code's available there as well, right? So if you're at the back of the room right now and you're thinking, there's no way I'm going to be able to see Ian's slides or the code, you can always grab it and look at your laptop near you, right? Anyone want to take a photograph? You done? Ready? Good? Okay, cool. Why do you care? So when we talk about cloud native, you quite often see some diagrams about kind of Pivotal has one, for example. Talk about cloud friendly, cloud ready, etc. And cloud native is kind of the epitome, right? And one of the pillars of cloud native is described as 12-factor apps. Okay. They're saying effectively, if you want to be cloud native, that's the style of application you should be building. Right, so what is cloud native? Okay. So I think the first question really to ask is, what do you mean by cloud? Who's running their kit on the cloud right now here? Okay. Who's not running their kit on the cloud? That may be a better question. There's a small number of you. And are you not running because you data center you're at such scale that data centers are more efficient, or just not got around to that kind of, or you have such a sunk investment in kit that you can't switch? So elastic, on demand, and self-service. So there are there's the three characteristics that are key to cloud success. The first is it's elastic. In other words, I can eat as much as I need, or I can slim down as much as I want. So I can respond basically to the success of my application or business by provisioning additional capacity, or I can effectively slim down when there's no one actually there and save money. Okay. It's on demand in the sense that if I have a traditional model in a data center, so some of our kits are actually still in data center, and what happens there if we want to expand our capacity is we basically phone up and say, we need another server. And they say, good, we'll buy you one. It'll be in the rack in about 6 weeks' time. Raise a ticket. So you get the rack, it appears in the rack. Then you say, is our new service here? So we've still got to basically install it all and wire it up, and another 2 weeks. So it's not really kind of on demand, right? So then that gets you into what a capacity planning, where effectively you as a software architect or an operations guy have to sit there going, well, given there's an 8-week lead time, I obviously need to predict ahead of the point where I'm going to need that piece of tin, that I need it, right? And that's much easier on the cloud because essentially I just say I need a new piece of tin and someone is spun up for me. And it's relatively short time window, depending what platform you're on and what operating system you choose, for that to actually happen. Okay? And it's obviously self-service, right? I just press the buttons and make it go. I don't have to make phone calls and put in tickets. I don't have to send someone down into the bowels of the air-conditioned basement to go and do the work themselves. I mean, there are other positive issues for businesses around things like CapEx versus OpEx, etc., but it's not really relevant to our conversation. But the key things we want to talk about is the fact that we could see the cloud as being elastic, on demand, and self-service. Okay. And so by cloud native, we mean, first, it's been designed to run in such an environment, right? We are saying we are going to run an environment which is elastic. What does that mean? What does it mean to be the fact that essentially we want to spin up new instances, right? It's on demand. We want to do that basically by saying now, I want a new instance of application now, and self-service. I want basically a new instance of application. I want to press a button to make it happen, okay? And exploits that environment. So it's an application that says, given that I'm running an environment that has this ability to be elastic, on demand, and self-service, how can I exploit that? How can I make basically that work to my advantage? Okay. So Pivotal has a maturity model. Everyone has to have a maturity model, right? For all basically things that we look at. But it's not a bad one. This one, Pivotal are kind of one of the people that really push around cloud native. My only problem with it a little bit is that cloud native says that microservices and API first design are what you get when you are cloud native. I think that particularly microservices is a useful tool to help you get basically to become cloud native, but it's a different story. But cloud ready is essentially talking about saying we're recognizing that I'm running on a virtual machine, maybe or a container. I don't necessarily have permanent disk access. And the platform was managing my ports and networking. I need to do this just to lift and shift. Right? Cloud Friendly says essentially, right, now I'm going to try and leverage the platform. So I'm going to build a 12-factor app, I'm going to try scaling horizontally, and I'm going to use the platform for availability. That really means looking at things like replacing, say, RabbitMQ with SQS and SNS on an AWS or Azure Service Bus, right? Saying, why am I doing all that hard work myself when you'll do it for me? And then effectively we get into cloud resilient, when we're trying to say, well, there's weird stuff happens now I'm in the cloud, like I get partition failures. When I was on my rack, it was all well and good, right, effectively, because I may have had multiple machines, but I never had network partitions between them. Suddenly now I'm actually on the cloud, all that cap theorem stuff that I kind of thought, this never really happens, suddenly seems to be happening a lot to me, right? So this is all about resilience. It's saying, I need to actually understand how to deal with those kind of distributed system issues because I'm running in that environment. And finally, get cloud native. Okay. So, a lot of what I'm seeing is people saying, actually, this stuff is not just applicable if you are running in the cloud, but it's also applicable if you are thinking about running your application in a containerized environment, so Docker, K8, whatever, etc. Right? Because those environments are also trying to say, well, I want to basically maximize the resources, and I want to do that in an elastic, on-demand, or self-service manner. Okay. And what they're saying is essentially, here is my pool of hosts. Within that, I want to basically be able to elastically expand a given app. In other words, create new instances across my pool of hosts. And I want to essentially do that in a self-service manner that's on demand, right? Quite often actually responding directly to pressure on the application itself. So even though a lot of people, you hear the term 12 traps talk about in the context of cloud native, be aware that it's also very, excuse me, very useful if you're in a kind of a container-based environment as well. Okay. Who's running Docker at all? Anyway, non-production, production. A few of you. Who's running Docker in production out of those people? And you K8, Swarm, Nomad, what are you? Okay. Sorry? Okay. So it's not the topic of this talk, but you'll notice people like Handsome and blogging about containers. You know, she's noticed that recently. Yeah, she's got quite a people like that. So containers are a significant change that you will probably want to be abreast of and on top of. Particularly as we get into the world of things like microservices, where containers are now being seen as essentially a deployment mechanism aligned to that kind of movement. And some people are saying that, you know, K8 is as significant a development in the industry as Linux. So, yeah, it's worth putting that in your to-do list for the year is containers. All right, and what the focus of really 12-factor apps is to a large extent, what the focus of cloud native or containers is to a large extent is elasticity. And that's really what we'll try and show you how we work towards that kind of elastic model tonight with our 12-factor apps. Okay. So you don't have to read this, don't worry. Just a screenshot for example. So 12-factor apps originally started at Heroku. So Heroku are a cloud provider, a platform as a service provider. Originally they basically started in the Ruby world, but now they're basically more Polyglot. And there's a guy called Adam Wiggins, one of the co-founders. He's no longer with Heroku. He's out in Berlin somewhere, I think. He looked at essentially apps that have been deployed to Heroku over time by various customers and tried to isolate what made some of them more successful than others. What were the common patterns and approaches they used which made them more successful? And the 12 factors were essentially distilled from Heroku's understanding of success. What did it take to be successful in the cloud? How did you do it? So they published this article then to say, hey, if you want to build for the cloud, bear these things in mind. Okay. So, again, the 12 factors themselves, there's an overall set of principles that 12-factor apps are fundamentally aligned to. So the first thing is that really one of the things that they're trying to get towards is this idea that says, I come and sit on your team on day one of my new job and I want to start working. How easy is that story? Right? Because really the ideal is, I say, where's the repo? And you say, here you are, here's the address of the repo in Git. Great, I'll Git clone that, I'll build it, and I'll run it. That took me 5 minutes. I am ready to begin as a developer at your organization. How many of you had stories like that today? Right, okay. How many of you have stories that are more like, yeah, on the wiki somewhere, someone documented the last time they did this, but it's kind of out of date over the last year. There were some emails sent around about that. I remember now. If you search for Matt, I think he sent an email around about how you install certificates to get the right. Who has stories like that more? Okay, right. So that's one of our goals, is to try and prevent that happening. Have a clean content underlying operating system. What does that mean? Well, to be honest with you, that nowadays it's a little bit hazier. But what we're really saying at heart is, I want my application to be deployable without the use of things like application containers like IaaS. That's the root of where they're actually going to with that nowadays. Modern cloud platforms. So the other thing here is really that I don't care very much about the underlying infrastructure I'm deployed to. I'd like to be agnostic to that as much as possible. Really, I want to basically say, I don't want to touch that at all. I would rather be independent of it. So this very much align with the container world of saying, if I run in a container, I don't really care what operating system that container uses, right? It's just a sandbox process. It's not a virtual machine. It takes some kernel libraries and binds them into my application, right? But declaratively, all I really care about is a certain number of small touch points that basically give me an application that I can run. And what we're saying is, over time, the operating system fades from our view. We don't really care. We care about running the CLR or the JVM or the Python, runtime, etc. But I don't really care about the operating system that provides life support to me. And so that model is increasing in that your application needs to be as divorced as possible from understanding the underlying platform. So things like talking to the file system, for example, and how you do that, right? That needs to be stuff where you need to start moving away from taking dependencies on the expectation that you're deploying to a given environment. And then minimize the divergence between development and production, enabling continuous deployment for maximum agility. So some of this is about the fact that, does production look like staging? And the answer in a lot of cases outside the cloud environment is no, because generally I can't afford to have two sets of kit that look the same. In a cloud environment, this is actually more practicable because you can spin up a set of an environment that looks similar, but even there, that's not that common. But it's also about some things that are not necessarily so obvious from that statement. For example, if my current version of the source, kind of the apex of where development is a long way removed from what's running in production because of time, we don't release that frequently. That creates cognitive dissonance for your developers who, when they see a production problem, now have to remember how the code used to work 2 months ago when the last time they released, rather than all the changes they made in the last 2 months, right? So it's also about things like frequent releases. It's also about not having different personnel, the kind of DevOps movement, right? Working basically in those different environments up and down the stack of your release process. So the more differences you have, the harder things get for you. And you can't read in the back, scale up without significant changes to development architecture or tooling practices. In other words, I want to build an app that will scale from the get-go. Right? I don't want to have to suddenly say, wow, we need to rewrite the whole thing now because we're going to have to scale it. Okay? So how can we try and avoid that problem right from the beginning? Okay. So what are the 12 factors? Because you've been sitting listening to me quite a while now, and I haven't mentioned any of the 12 factors, so you might have some idea what they are. Okay, that's list 12 factors. So I won't read them out because you can read. But I've grouped them into some colours. So I've done that because I think they're easy to talk about in groups. So one group essentially really is about how we design our application, and that's the group in green. Okay. Those are some constraints we're going to basically ask you to follow at design time, to how you structure your application in terms of dividing it into modules, and how you actually host your application such that we can meet some of the 12-factor goals. The blue ones are essentially about how we build our application, and they're really about that model of making it easy for developers to join the team, making it easy for us to essentially minimize the divergence between production and other environments. And well, this is about running. Ones in red are about running our application, right? We'll talk less about these tonight, just for time, really. That's a lot about stuff like saying we want to log to standard out of stuff. I'll come back to those later. I'll give you a brief, like 2-minute rundown of those, but maybe look them up. Okay. So let's start by talking about how we design two-factor apps. What are the key issues that we want to talk about? What may be different to what you understand? So the first one I usually talk about is what's called port binding. So port binding, anyone know what port binding is? Anyone have a stab at that? Okay. Export services via port binding. So here's the idea. When I have my application, it needs to talk to the outside world in some way to do something, right? My code is running, it's running on a machine. How does it interact with anything? So if it's a web server, essentially it communicates with the outside world by, say, port 80, port 443, right? So essentially it listens on those ports and it interacts basically with those reports by request and response. So in the case of an HTTP app, it's very straightforward to understand. What I want you to do is essentially say, I'm going to run an application, and the way it's going to talk to the outside world is it's going to essentially have ports. When we say export via port binding, what we mean is the application itself should say, I want to talk to the outside world via a port, but the act of effectively choosing what ports they are and the URLs that they are located at should be something that you actually do when you just deploy the service. Okay. So those of you who looked at something like Docker obviously essentially mirrors this kind of model in the sense that whatever you run inside a given container, you can choose to essentially change that port on the host. So you may be exporting effectively port 5000 from your container, and the host may say, well, actually, I'll treat that to the outside world as port 80. So you bind differently. But essentially the idea is your simple little application, its first protocol would be to say, okay, I'm going to have a port and I'm going to receive requests over that or return responses to that. Don't worry, this will make more sense in a little bit. The second thing is it should be self-hosted. All right. So I don't want to have some kind of thing that my app has to run in. I want to be able to just basically press, to run the executable or whatever basically, or run the interpreter and run my code, spin it up and get it going, and it starts listing on the port for me. Okay. If I have multiple parts of my application, then the way they talk to each other is by essentially the fact that the other application is exposing a port, right? So you come in and call my web service basically on port 80, and it says, oh, in order to service this request, I'm going to call a couple of microservices. That's fine. They'll be listing on ports too, and I'll call them via HTTP. Okay. So everything is talking to everything else via a port. So while we're talking about HTTP at the minute as an example, because it's fairly common ground, we don't necessarily have to be using HTTP as a protocol. So for example, I may decide that 2 of my apps will communicate via messaging rather than, say, HTTP/JSON or REST, in which case essentially I'll be using an AMQP protocol, but I'm using a different port. I can't remember what Rabbit's default is, 4372, something like that, I think. Right. So again, I'm talking to a port, I'm listening on a port basically for messages, right? Or I'm sending messages to a port. You connect to the broker over a port, you say, here's a message. But I'm still listening to ports. And the key to understanding this idea is this line at the bottom, right? So I'll read it for those at the back. Avoid hosting an application server like IIS. So one of the things we used to do a lot, particularly in the sort of Java and .NET world, was we ran in application containers, IIS or JBoss and all those equivalents, basically, or Tomcat, Apache, right? We ran these big beasts. And the problem with that is it doesn't really work in the modern world. It's kind of a falsity. So you want to get away from that and say, actually, my little app will host itself and just expose some ports. And let me explain why. So this is IIS. Everyone kind of familiar with the IIS diagram? Yeah, joy. Okay, so the call comes in from the internet and it hits HTTP/sys, which is part of the operating system on Windows. And then it says, okay, what I'm going to do is I'm going to go to the service host exe. And service host exe is basically publishing service, and I ask it through the application host.config. The application host.config will tell me about all the sites that IIS is hosting. IIS will then say, oh yes, I'm hosting all these sites, and the way that you instantiate this particular .NET site, effectively, etc., is you're going to use the Windows Activation Service, rather, effectively, to run this W3 worker process, or one or more W3 worker processes, and that will effectively load up your application and run it. Okay, and then you get all sorts of complexity here, where essentially, which are important to the conversation around, well, I may have multiple threads, may have multiple processes. Generally, the thing to take away to understand is generally what happens is we run a number of processes inside the container. Okay, so it's not uncommon for you to have essentially 4 or 5 different sites potentially running on one instance of IIS, okay, or effectively at least subsites. And so you're saying, well, I'm going to run W3 with WP, and I'm going to run all these things, and I'm hosting them in this container, right? And that is how application containers work, and you can find different variants in different languages, right? This is Docker. So with Docker, I have a Docker host, right? So it's a Unix box, effectively. And in my Unix box, I have something called the Docker daemon. So basically, that's a process that runs basically in the background. And you can talk to that from the Docker client. We'll show you that happening later. And the Docker client essentially can read Docker files, essentially got a whole range of commands: run, exec, Docker, I should have a D on it, Docker PS, right? So basically, you talk to your Docker daemon via a REST API, effectively, that exposes outside of the host. And then what happens is, in response to the instructions you've given it, we'll go away to a registry. We'll basically grab an image. We'll use the image to create a container, and we'll spin up a whole lot of containers. So what's a container? So a container is not a VM, right? That's the first thing to understand. A container is essentially a sandboxed process running essentially on the host. That's why effectively you can have an entirely different flavor of Unix in your container to in the host. It's because essentially all that really matters is the kernel. And you basically build a set of libraries into your container that do things like say, I want to access the file system, etc., or other operating system-based services, and that allows you to run. The advantage is, of course, when any one of these containers essentially falls over and dies, it's sandboxed and won't take anything else with it. And effectively I can do the other thing, which essentially is I can say, well, I've got whatever computer capacity I have on the host, I can share it basically amongst these various containers, and therefore I can maximize my usage of my instance. So I don't know if you know, but I think roughly on average speaking, the utilization of a EC2 instance, for example, in AWS is somewhere around 30–40%, which kind of means 60% of that money you're just giving to Amazon, right? The other 30% you're actually paying for, but the 60% of it is just idle. It's not doing anything. And part of the pressure towards containerized workloads is to actually move that number all the way up to about 90%, right? To try and say, I want to increase the utilization of my existing instances. And people are talking about halving, effectively, their costs by doing that. But you can see that in this model, I've effectively got a set of containers, right? Would it make a lot of sense for me to run IIS in one of those containers? Probably not, because IIS is doing pretty much the same thing that this is doing, okay? IIS is essentially saying, hey, I've got basically a whole set of containers and I'm going to run them for you in Spencer's demand. So our alternative approach here is to say each one of these containers talks to the outside world over a port. It says, I'm going to expose ports on the container. The host effectively can remap that, expose that to the outside world, but these ports let you effectively call in and get hold of these sandbox processes. And I can deploy them to multiple hosts, and when they appear on that additional host, they just say, I use this port, and I'm bound to that port right on that host for communication. So that's why we basically talk about port binding, right? Because your apps are starting to look much more like this and much less like this. Treat backing services attached resources. So what is a backing service? This is the second kind of like principle. So a backing service is anything your application talks to. So the obvious thing is all the other services that you've built, right? You've got your microservices architecture, obviously, because why not? And you've built 10,000 services, your Twitter, and you're looking fondly at your Death Star diagram, effectively, of all your services to each other. I think it's a good idea that way, that approach, but all those things are basically backing services to you. So anything you talk to over a port is a backing service, all right? But there are other things that you might want. Your database is essentially a backing service from the point of view of this. I talked it over a port, right? It's a service I talked over a port. I just say hello, right? Particularly if it's something like Mongo or whatever, God forbid. And essentially, I'm talking over that via a REST API because that would obviously be the way to talk to databases. But it's another service that I talk to. But there are others. Your file system. Okay, in the cloud and in containers, you cannot rely on the file system on the instance that is running your code, right? That file system data is not backed up anywhere useful for you, okay? When the machine goes down in AWS, so basically what happens is they put, cheap as chips machines into shipping containers and wait for them to fail, right? And they will fail. When it goes down on you, all the data on that file system is lost as you backed it up somewhere. So generally you don't do that. Generally you do something like create elastic block storage or S3, depending on your storage requirements, and you store your data out there instead, right? So you say, well, the ability to use a file storage is a service, and I'm going to ask you for that service and store things to it. I'm not going to assume that an operating system dependent file system is the way to go. So I am breaking, as we said earlier, my relationship with the operating system. I say, I want to store stuff, I'll ask for the storage service. Right. Same is really true a little bit in containers, where you don't tend to talk to the file system in the container very much, because it's ephemeral, or map something on the host. What you tend to do is create volumes. Talk to volumes instead, right? And that tends to basically mirror the same way you're looking at talking to EBS. So treat them as services, right? Anything you need is a service that you have to talk to. In serverless environments particularly, so serverless environments are just containers, right? If I'm in an AWS Lambda or a Azure function, what's happening is just containers. So what happens is your code is placed into a container, there's a pool of them. Essentially, one of them is spun up in response to basically something coming in over a port. Remember that whole thing about ports again, right? Something comes in over a port. An instance is spun up, or one sent to me out of a pool. I get it. I can do some work on it. It's returned to the pool, right? Next request comes in. I may get that same container. I may get a different container. I may get a new container. I cannot rely on what is on the file system on the local file system in an AWS Lambda or an Azure function. Now, some folks are naughty and they say, oh, I'm going to test to see which one I got back, and I'm going to play around with the file system on the container, because you can access it, same way you can access a container. I can write code that calls it because the underlying container goes, yes, I can do a file system requests. I'm going to write it basically here. But you don't really know where that is. It's ephemeral. It may be on the host, but you've got no guarantee of whether you'll be moved to a different host, right? The scheduler may just say, I'm taking you off this host and I'm putting you on this host, right? Goodbye to the thing you wrote locally to your file system. So you don't have that guarantee anymore. So all the things that you depend on have to be treated as a service now. Okay. Always assume you need to provision any storage that you want to use, right? You're going to have to ask for it as a service to get provided to you. Make sense? So we looked at ports and backing services. Right, okay. Let me do a quick demo then. This is the world's most over-designed Hello World application built by me. So we basically it's a .NET Core application, and we essentially have, no, I don't want that one. Let me just switch the versions in GitHub. Make it a bit simpler, make it app only. Oh, yes, because I've got an out directory somewhere in there. Hang on. Let me just, because I was actually checking it all worked, I've created a few out directories. You'll see me create those later, and a couple of them will stop me. One of them somewhere has got itself into the Git repo. I don't know why. And that causes me problems. Nope. Okay. Let's just. Okay. Right. So, ignore Greetings Worker because it's basically been pulled down, but never mind. Greetings App and Greetings Core are all you care about at the minute. So Greetings App is basically the SPNet core site, and Greetings Core is a set of libraries that go with it. So Greetings Controller is essentially, so the idea behind this site, I will show you essentially the test file, is that we're going to basically post hello worlds or hello Mary or hello Bob or hello Sue to the server, which is going to store them for us so we can see all of our greetings in future. A fabulous application which will obviously make me a lot of money after I have my first initial coin offering. Okay, so you pretty much what you expect from a controller. We've got basically a set of REST endpoints we can get essentially by ID, get all of them. We can post a new item, we can delete it. This uses, because it needs to be over-engineered, some libraries I work on called Brighter and Darker, which is basically a CQRS framework. Fairly straightforward to understand. Let's go post. So the command process just says wrap up basically the request we've got from the outside to say here is basically a new greeting. Turn it into a command saying here is a new greeting, and pass it over to our command handler effectively, which will deal with it for us. And these command handlers are essentially over here in here. Partially it's just so I can show you something other than just fed to app code. So what happens here is we say, well, we're going to take that basically command, we're going to spin up a entity framework context, we're going to essentially create a little repository, and in that repository we're going to add a new greeting based on that command, right? All code you've kind of seen before, I'm sure, 1,000 times. We're all obviously at a completely async pipeline because this is, 2017, and we like to be async. And these reliability aspects that you can see on it are just basically something Brighter does for you. It builds a pipeline, and you can essentially insert things in the pipeline. So let's just run some poly policies to do things like retries and circuit breakers. So you can see all that if you go and look at Brighter. You can see how that works. Okay. So as I say, that's probably the world's most over-engineered Hello World app. Okay. So the other thing to understand here, we've got basically a Docker Compose file. Who's seen Docker Compose before? Just okay, not too much explanation, right? Okay. So obviously we've got a number of services here. We've got web and we've got MySQL. We're just using MySQL because its footprint is lower than SQL Server in a container, so it's easier, less pain for my Mac. And essentially, so it's a database, effectively, what talks database. The interesting things to understand is what we're saying here effectively is we are exposing this port 5000. It's actually something in our application runs on 5,000. We're exposing it as 4,000. You can see we're doing the same thing here with basically the a database. So both of them are running on ports. Their environment variables. Just note that we'll talk about what those are later. Essentially, Compose is to build a network. So we're effectively saying the web can see basically the database, right? We have a depends on to make sure the database is up before we start running a website. Okay. So what I'm going to do is build that. So I'm just going to, what I'm doing here, the technique I'm using is just to build locally and via publish, really, essentially out to an out directory, and then we'll pick that up and we actually build the application in Docker. So you can see we've got a few Docker files in here as well. I think there's one or two. These are useful to see mainly because you can see the declarative nature of what we're talking about 12-factor apps. Right, so essentially we're saying expose the port 5000. That's how we communicate with the outside world. This is port binding, right? And that effectively gives us the way that we talk to the outside world. Right, let me just see if this is going to build for a second. So Docker's going to do its usual check. I've already basically got downloaded images because who knows what kind of connectivity I might have had. And you can see there effectively I've got MySQL running and I've got the web running, right? And you can see down the bottom, potentially, I don't know, you might stand up at the back to see it, but those of you who can see the bottom can see that it says I'm listening basically on port 5000, right? So this idea that we're basically listening on ports and we're self-hosted. And you can see that in the code over in Program CS. This is, of course, how essentially in an ASP.NET Core application we spin up Kestrel. And that says use IIS integration, that's just for debugging. But we're not hosting an IIS at all here, right? It's just Kestrel standing on its own 2 feet and saying we're going to expose basically app on port 5000. Now, in a real app, you want to put Nginx in front of this because you want to do things like SSL termination properly, etc., or proxy caching. But for our purposes, will work fine. Okay. And then, actually, let's put up another window. You should be able to see we're running effectively. Hang on. Is that okay at the back? Yep, cool. We're running essentially here effectively the MySQL on the web. Okay. Now, so what we're going to do, I think I've got a few in there already. We're going to fire a request to the database, and we're going to get it to bring back to us essentially what the contents, what greetings it's already got. Okay. So you can see Kestrel's responded to us with a 200. We already have a range of greetings that I've been testing over time. The database is mapped to a volume in Docker Compose automatically in the MySQL, and that means essentially it will persist between actually requests. You don't have to do that yourself. It's just part of the MySQL that you got image. Okay, so let's want to put in hello Alice. I can do hello Alice. Right, I get a post request, get a 200 back. Basically, it tells me basically what I've just created, and I can then go away and I can see Alice. Okay, at the bottom. All right. And if we go over here, let's make that a little bit bigger. Then you may be able to see those at the back. This is a bit awkward. There's nowhere I'm scrolling it up, but you can see that the web one is essentially responding to requests. When I'm running inside a container, I'm exposing a port. I'm talking to the SQL database, which is just under service, exposed by a port, right? And I am essentially ephemeral. I'm inside containers, and so I'm not relying on any of the underlying services. Okay, processes and concurrency. So most of you have heard this before. So what you want to do is execute your app as one or more stateless processes, and the stateless is the important part of this note. So we're going to scale in this fashion. Right, we want to be stateless. Why do we want to be stateless? Well, state unfortunately prevents you from scaling, right? Stateless is a bad word, by the way. We should really probably say state aware more. So apps that are stateless don't deal with state. What it means essentially is you're going to go to a backing service and retrieve the state or pass the state around inside your HTTP requests, but you're not going to store the state locally on one individual server. The problem with storing it locally on one individual server is, of course, that you then have to have a sticky session to that server. Sticky session to that server is not going to scale because I can't redirect to the traffic that's overwhelming that server to new servers as I bring them online. Okay, so we're always stateless in order to give ourselves the most flexibility to be elastic. I can't be elastic without being stateless. I have to be able to redirect the traffic to all of my nodes when they appear, not specific nodes. You can use basically the file system memory space for a per session kind of cache. In other words, if the request comes in and I want to basically shove something away in memory and then later on, a few steps later, access it, that can work, right? Because you're saying within the context of that given request and response lifecycle, I want to use the file system or the cache basically to hold some values for me. But don't use basically local resources for that. If you need a file system, you look at S3 or EBS, something like that. If you need basically a cache, look at Elasticache, Redis, a distributed cache of some sort, right? It's a backing service out of process to you. Okay. Task queues. Anyone knows what task queues are? Well, you can use different processes to handle different workloads. So one workload is the HTTP request coming in. Another workload might be effectively a long-running background task being handled by a worker process. Okay. An application may experience peaks of demand that cause it to become overloaded and unable to respond. Okay, so this is what happens. A request comes in, another request comes in, another request comes in, and for some reason my application is slow. A typical reason might be I've got resource contention on the database, right? It's quite nearly always the database is the source of your problems. And I'm waiting to get basically my connection from the pool in order to do my work. After a while, essentially what may happen is I may begin to either shed DB connections because effectively I can't find one in time. So you start to get errors saying DB connection timed out, and effectively you'll frustrate requests. Or essentially you'll have a lot of pool stuff, but the thread switching between them will mean essentially that nothing's being served for a very long period of time. You spend your entire time context switching, and eventually you can't meet new requests coming into your application. Eventually at some point you'll queue, and then you get a yellow screen of death. Has anyone seen DB connection pooling issues at scale? Anyone seen yellow screens of death? A few of you have? Okay. All right. This other application, one of its dependencies becomes overwhelmed by the sheer amount of traffic, right? So the solution is to offload some of that work. So generally we have a rule, for example, at Hardware, you can't see at the back, it talks, I can explain what the rule is, saying that really any piece of work must execute under 300 milliseconds or you offload it. 300 milliseconds is roughly a good rule of thumb for the ability of your web server to respond quick enough that it isn't overwhelmed by the rate of incoming requests while it's processing current requests. Okay, that's generally your problem. If your incoming requests exceed the rate at which you're dealing with the request that you already have, effectively you will get a backlog of requests which eventually will overwhelm you. So as soon as you start to have some feel that you're getting a backlog, and this is a rule of thumb, but you may find that essentially that even that's not enough, one of your options effectively is to load balance, right? To say, I'm going to hand this out by increasing the number of instances of the web process that I have. Okay, so you say, I'm just going to keep upping the number of processes. And that's actually not a bad, approach in an elastic environment, because you say, well, I just put up a new one on demand, okay? But that can get expensive. The other alternative is to start saying, well, I'm going to queue those requests and deal with them in my own good time. And what I will do is give a response back to the user to indicate that I have received your request, but I've not yet completed it. So if you're an HTTP to accepted, you say, I've received your request, but I haven't finished it. And you give back a link header that says, you can go here to monitor basically the outcome. And at the end of that link is either a resource that either says 60% done, or whatever progress marker you want to use, effectively, or effectively says, well, I'm 404 because I am the resource you're creating until you can finally recreate me, at which point you do a redirect to recreate it. Okay. And the way you offload those requests is generally to use message-oriented middleware of some sort. Though you can build this stuff on things like Redis, right? So you say, I'm going to take this work, I'm going to put it on a message queue. The work's being received at a variable rate. And then essentially, because I can control the rate at which my worker process reads off the queue and processes work, I can turn that variable rate into a constant rate. And that constant rate is nicely predictable, because I can say, well, I can support 5 worker processes. And it means I don't get an unexpected bill from Amazon, right? So what I get instead is basically I know that I'm running up to 5 worker processes, and that's where I'm going to stop, and everything else just basically queues up waiting. Now obviously the downside of this approach is that obviously somebody's work is being handled asynchronously and you can get eventual consistency issues. But from the point of view of many requests that your users will fulfill that you can't do under 300 milliseconds, actually user expectation is quite often, this would obviously take some time, I'll come back and look at it later when you're finished, right? So you can just give them a response that says, I can figure that out. Okay, so that's a task queue. Put the message onto the QA service endpoint. Consumer reads from it. Queue stores eventual processing. So talk about guaranteed and at least once. So guaranteed delivery says, I will eventually give you this message. I've received the message. Thanks for, you put it on the queue. I've received your work, customer. I will get to it. It's guaranteed now. We're going to keep this one for you. And at least once. At least once means a consumer will be delivered the message. So there's a difference between at least once and exactly once. So exactly once says there's one message, one consumer will get it and they'll process it. Okay? At least once says there's one message, at least one consumer will get it and process it. So that's with distributed systems and how we actually cope with basically failure. So for example, in some cases, we don't know whether or not somebody received it. We may have to resend to everybody, in which case effectively you may receive a copy because you didn't know whether anybody actually actioned it, right? But there are ways of effectively achieving exactly once if you need to. Otherwise, you tend to rely on idempotence. In other words, essentially I can replay the message another time to avoid essentially the issue of that replay causing you problems. So you can do that by things like, have I seen the message before? Is the ID in a database? Discard it. Actually, if I reapply this change, it will be the same, so it doesn't make any difference. So the QX is a buffer that basically allows you to split the rate of consumption, which makes it easy to do capacity planning, right? Yeah, and you have to control the rate of processing of those spikes down the wire, right? Okay, I will show you how a queue works. So although I work brighter and the reason I was using bright and darker earlier is bright and darker basically support this for you. They support task queues. The mass transit and service bus are the other things that basically you may well have heard of that basically support this model as well. If you're in the Python world, Celery basically. If you're in Node.js world, Seneca would be equivalent tools. Okay, so let me switch to a version that has app and worker. Come on. App and worker. I don't think app and worker's right, so we had that worker that we didn't really look at earlier. So we're going to look at worker now and have a look at what it's doing. So we won't go into too much detail on worker, but essentially a worker is just another process that we can run. It's a .NET process again, effectively, and it's got an entry point, but it's not explicitly looking at a port there, and we'll show you how we do that later. So essentially it's just a console application. So nowadays we tend to use console applications a lot because you want to be cross-platform. Obviously things like Windows services don't exist. So you have to rely on something else to keep you up in a Unix environment. Either in a container you don't bother because the container itself is the unit you can restart. Effectively it's a service. Or if you're just on flat Unix, you stuff like supervisor. Okay. So essentially what we do in our main is we create basically a thing called a dispatcher, which is a thing that Brighter provides for you, and we say receive. That just means basically we're going to receive messages from a queue, and effectively we'll keep doing that until basically you hit a key, at which point we'll stop effectively and we'll end. Okay. So most of this code is just configuration of that, and I don't want to basically bore you with that stuff. But this is the thing that's worth having a quick look at. So the dispatcher is created by this Fluent application. And down here you can see what we're saying is we're going to talk to a connection. Let's see if I can move that up enough so anyone can see it. And that connection effectively is exposing some information from Rabbit. And it's saying, here's the name of the connection as a routing key. So the key thing to understand on Rabbit is, on say RabbitMQ, I subscribe to a topic, the routing key. And I say to Rabbit, give me all the messages that match that. And what it does is it creates a queue for me, for my application, and it passes down my copy of all of those. So a sender or a producer sends to Rabbit a message with the given key, and everyone that's subscribed to that key gets their own individual queue down which is passed. Okay. However, I can share that queue between multiple consumers so that they can process that queue, because you can lock individual records as you're working on them, and then the next consumer gets the next item in the queue. Okay. So we're just going to create some queues and we're going to listen on them. Right. Now, you'll see that what it's doing there is it's talking about a regreet command. So a regreet command is something new we've added in here. Right. Oops-a-daisy. And our regreet command effectively is just this command that essentially says, I'm going to give I have a GUID, and basically I'm going to say here's a GUID value. It's naughty, but it works. And when I basically add a greeting, now I'm going to say raise a new regreeting command. So basically Brighter gives you some stuff as well as to read off queues to post to queues. So earlier we were using a send, right? And that just says handle it in process. Post means handle it out of process. So it's going to say put this onto send this to basically to RabbitMQ. Then the worker process will read that off the queue and do some work with it. And the worker process is simply going to write to the console when it receives that message. Okay, and it's going to put out the greeting ID and the greeting message it received. Okay, so this means that when I run, where's my tests HTTP file gone? Hello, test HTTP. Where are you? Where have you gone and hidden from this file here? When I run this time and add something, what should happen is that will go to RabbitMQ. And when it goes to RabbitMQ, it will then effectively, the consumer will then read that basically off the queue and then handle it. Okay, I'll show you Docker Compose. The other thing in Docker Compose to note is essentially we've got a bit more complexity in here. As well as the web, we now have a worker role. Okay, we also have RabbitMQ here, and we have basically MySQL. So we have some more infrastructure built up. And the worker effectively has its own Docker file, which we saw earlier, just basically flat.net, exposing an entry point that's been built. Okay. You can see we're also using some environment variables. Okay. We'll talk about this a bit later, but one thing we don't want to do, essentially, is rely on configuration files. Okay. So by using environment variables, we're very easy with something like this container application to set things that point to other parts of our network. A better alternative in production systems is to use a configuration management server like etcd or console. But that topic is a bit later in the slide deck. But I just want you to note that briefly now, and we'll come back to that topic fully later. So what I'm going to do, hopefully I've got time to do this, is I'm going to stop these two, and I'm going to just build, because I've got some additional artifacts. I'm just going to build the additional projects, and then we'll basically bring it up, and you should see then when we do Docker PS, we've got a lot more roles this time around than previously. We've now got our worker process. So remember what we're talking about is we're saying we've got a web process, but we want to offload some work to a worker process. We're going to use a queue because that means we can simply say, I'm going to act back to the user and say, I've got your request. In fact, in this case, I've added something, right? I've done an add and added your greeting. I've got some additional work to carry out. I don't need to do that basically for you right now. I can do that basically asynchronously. So I post it onto a queue, and the queue can handle that. So although our request is very simple, you can imagine it's maybe doing something more complicated, like, for example, sending an email, right? That's not an uncommon thing. I want to send an email. I don't want to basically make you wait around while I call the SMTP server. I'm going to act back your request, put something on the queue, and from the queue, when I process the item on the queue, I will call the SMTP server and send out your mail to your given, your Valentine or whatever. Okay, being trying to be topical there. Okay, so we will do Docker Compose up build. So we'll bring up that suite. I may have to kill Rabbit. I always think I've got a local Rabbit. No, it's fine. Okay. So you can see all the workers and this is printing up. If we go into the other tab and do, oops, sorry guys, Docker PS, you will see that we're basically running a worker and a web as well as Rabbit and MySQL. Okay. So now when I go to test HTTP and I add a greeting, let's just do hello world for the time being. Okay, we should see over here, it's a little bit hard to see, but oh dear, connection mention a few, so that's early on in the process, don't worry. Okay, so again, unfortunately, one of the problems with doing these demos is that it scrolls to the bottom of the screen. I need about 20 other things for you before you can actually see it, those at the back. But can you see, essentially, we said we received a greeting message as follows: hello world, greeting from originator follows the GUID, etc. there, right? You can see up here, by the way, there's a whole lot of stuff we're pumping out, basically, by default out of Brighter for you. And one of the things we're pumping out is that we received a message, basically, from that queue, and that's the contents of the message that we received over the wire, right? So because we basically turn on info level debugging, you can kind of see a lot of information. But that's gone over the queue. If I send another one, for example, Alice, send a few. So we respond quite quickly, right? There's no real delay, effectively, to the response you're seeing in the other window. 27 milliseconds, 20 milliseconds, right? But over here, you'll see a whole range of these coming in as well, so you're offloading that work onto the worker process. So this is idea, essentially, we've got basically, what have we been through? We said, well, we're going to basically create these apps. And these apps are going to have a number of factors that will make them suitable for use in cloud or container environments. And we said a basic app will be a kind of standalone process that exposes itself via a port. And what we want to do is run one or more of those, and some of those will be maybe web processes, some of them may be worker processes, and they may communicate over different protocols. So HTTP to get in and out, sort of REST, or AMQP for messaging, which we just saw. All right, and we said, you know, some advantages essentially of this kind of stateless, these stateless processes is that, well, we can say, well, I'm going to hand this work off and run a different process over here, and that's going to do some work for me. But the other real advantage basically is that I can begin to use this to scale. And remember at the beginning of this conversation, we were talking about this idea of saying, you know, elasticity is the key to understanding what cloud is: elastic on demand, self-service, and that containers are becoming elastic on demand, self-service. So we haven't really kind of shown that at all, right? So how are we getting the elasticity? So all these individual little processes, what we do is we prefer to scale by creating a new instance of the process. Okay. So it's not to say under 12-factor apps don't use threads, right? But it's saying don't rely effectively on vertical scaling. So don't rely on essentially getting increasingly bigger and bigger and more powerful pieces of tin to run that one process on, with it spinning up more threads for the more CPUs you've got. Use a model where essentially you say, I'm just going to create more processes, because that enables us to actually work with things like schedulers much more easily, right? So in a world where effectively I have this massive multi-core machine, my problem essentially is I've got one of that machine, right? And it's essentially a point of failure. What I really want is multiple machines, so if I lose one machine, I continue to have capacity. And it's much easier essentially to have lots of small machines than it is to have one big machine in terms of that capacity that I'm providing. And if I have individualized processes, then I can allocate them essentially to that array of machines and say, well, you run here, you run here. And that's what this whole idea of kind of scheduling and orchestration is about, right? I'm going to guarantee I'm going to run 12 instances of your process. I've got 4 hosts to run them on. I will distribute them amongst those hosts. Okay, and now you've got your 12 instances. One of them goes down, I will bring you up to 12 instances again by essentially provisioning more of them. If I lose a host, then you're going to have 6 instances on the 2 machines maybe. But the process model lets us have some flexibility that we don't really get with threads. And because we're essentially stateless, we share nothing, then we just introduce more capacity by effectively introducing more threads. Okay. Now, obviously there are scaling bottlenecks, or there always are. So your database, for example, may be a scaling bottleneck. You may need to move to distributed databases, that kind of thing, etc. But and this thing about don't demonize use the operating system process manager. What we mean by that is the processes that we run shouldn't be thought of as demons in the Unix world. I mean, essentially Windows services as well, Windows world. actually rely basically on our ability to schedule the processes differently. So once we get into things like containers or even into the world of the cloud, really we're externalizing our ability to do that scheduling essentially to outside the application. Okay. Maximize robustness with fast startup and graceful shutdown. So if I want to scale, my problem is going to be that I don't want something where I say, I'm going to bring up a new instance in an elastic and self-service and on-demand manner. It will be ready in 10 minutes when it's finished building the model, right? That's obviously a problem because you can't react to scale at that kind of lag. The same is also true of our ability to take something down, right? I don't want to basically meet the peak demand of, say, 2 to 3 in the afternoon when the US and UK customers are all online at the same time, and then say, okay, well, we can take all the traffic down now because the UK has gone offline. Yeah, that'll be down in an hour, you know, right? Well, that's no good because that's what money we're paying for. So really, we want to be able to start and stop very quickly. So our process should make sure it can do that. Okay, start in a few seconds and stop gracefully. What do you mean by stop gracefully? Well, generally, if I want to kill a process, there's a question which is, what work is it currently doing? And there are two major strategies, right? One is take in no new work, but allow all the work I have to run out, or just essentially abandon the work that I have and assume essentially that that work will basically be resumed on restart of the application. Okay. So, for example, if I'm a web endpoint, there's nothing going to keep that request for next time around. So the best model would really be as I shut down to say, okay, I'm not going to receive any more HTTP requests, but I will service the ones that I have. So for example, if you turn like Nginx, that's Nginx's model effectively. Nginx will say, I will let the existing processes finish before I shut down. Right? There's nowhere for the work to go. Using a queue, you could just say, it doesn't matter, I can kill the process because if my message-oriented middleware doesn't receive an acknowledgement, it will leave the item on the queue after it basically unlocks it after a suitable timeout. So when the process restarts, the work will be available for it again to pull off the queue. All right. Interesting enough, on Brighter, which is the thing I work on queue processing, we actually follow the Nginx model and let the work run out. And that's mainly because we don't want you to lose the investment in time you've had already processing work. So we try and say, well, we'll take no new requests, but we'll process the existing work. That's sometimes controversial with people in Huddle because it means sometimes it's difficult to kill the process in an adequate time because it's doing some big job, in which case you have to go in and kill it aggressively by, burning it with fire. There we go. But, right. So you can see here the idea basically of competing consumers, where we're effectively saying, well, the rate of one consumer reading off the queue is not the constant rate that I seek. I've taken a variable rate and moved it to a constant rate, but my constant rate needs to be greater than I can achieve for one consumer. So I'll get multiple consumers to read the queue. So they're all going to read messages off the queue, and all I need for that is my message-oriented middleware to support the idea that if the first consumer is consuming this item, the second consumer says, well, that one's locked, I'll consume the second item, and the third consumer says, well, the first two are locked, I'll consume the third item, right? So you have to have support for that in your queue manager. You may think, well, surely all message-oriented middleware comes with that. So RabbitMQ will, something like Kafka won't, right? Kafka, you have to do all that kind of work yourself. Right, this demo is very simple. So one thing I can do with Docker Compose is I can say, well, rather than just have the one instance of my web or worker role, I'd like some more. Now, what we need to actually, I wonder if we do this. I think I've got one of these. Let's have a quick look. Right. Now this one uses Nginx as a reverse proxy. We may show that working. I don't know whether or not we will manage to get to see that. Okay. And so when I now do Docker Compose up, so I don't have to necessarily take down the ones that are currently running. It should figure out for me what I've added and then bring them into the mix. He said. And I can compose up, build. Oh, doesn't like the reverse proxy. Okay, we won't do that bit. We should have. That's an interesting idea. Yeah, doing it in that window. Okay. No, you don't want to bring up my additional workers, do you? Okay. Let's select to shut those down, and we will go old school and bring them up explicitly. Okay, all right, cool. Now, what I'm running here, as you can see, is a web and a worker. What I want to do is actually increase the number of consumers on my queue. So I'm going to, this time, pass in a scale parameter and say worker equals 3. This should, I get the syntax right, start up some additional workers. So you can see now worker 2 and worker 3. Now, when I come over to my tests and I add a new request, I'll add a few actually because otherwise it'll scroll to the bottom of the screen and you guys won't see. What we should see is a range of workers are now dealing with those requests. So we've got up here worker 3 dealing with Alice, worker 2 picks up then Alice, worker 3 is picking up Alice, and worker 1 is picking up Alice, right? And so up here somewhere there's probably actually some other ones. There's Mary basically from worker 1 and Mary there. So can you see that what's happened is that the multiple workers are now picking up work. When we basically raise that greeting, that regreet, then what happens now is that there are 3 workers, and those 3 workers are all reading from the queue. So when we send any one message through, any one of the 3 could potentially receive it and start working. So that one's gone basically to worker 2. And that one's gone to worker 1, right? So what happens is they're reading in turn. So that's effectively given me scaling by just saying increment the number of instances of that process that I have. Make sense? So there's a demo here I won't actually do, but just because I don't have a set up to internet connection and stuff like that. But I'll tell you what would happen, and it's fine. You won't miss anything. So let's talk about design factors. So we're talking about essentially how we build our applications in a 12-factor app model to really take advantage of the elasticity that's available in cloud or container environments. So we build them as processes that listen on ports that are self-hosted and that talk to everything around them as a backing service, assuming that the environment that they are in is essentially not to be dependent on. And may have separate web and worker roles or other roles basically, but beyond that, and that we scale these stateless processes by simply increasing the number of them. Right. Let's talk a little bit about some things that are recommended really around how we build and release our software. So this idea of one code base and revision control many deploys. So essentially when I come into your organization, what I want to do is I want to say, where is this app? There's clearly a repo that app belongs to. And I go and do git clone and I have the app. I don't go git clone on 12 different repos, and you say you have to build this one, then that one, then the one other, right? Effectively, etc. Doesn't work like that. It's just one repo. That's our app. And essentially, yeah, one app is one repo. Multiple repos are a distributed system, right? If I've got multiple repos, I have a distributed system. There's a bit of controversy at this point, and the controversy is about web and worker. Okay. If I have a web and a worker process, and they're working on the same workload, is that one repo, or effectively is that two repos? Is it because they're two processes, two different processes, they ought to be two repos? Kind of depends on your model, I think. So we have a model whereby we say that that worker process that you saw earlier is part of the same bounded context as the web process. It can access the same domain model, and therefore essentially ought to ship along with the web process. It's what we call a continuous integration boundary, because if I change the schema, say the underlying database, both of them will be impacted. So they must therefore be part of the same CI boundary, they must ship together. So we would say, if it's part of the same CI boundary, effectively, it's part of the same bounded context, then basically they're both part of the same repo, right? If effectively they are not, then essentially they're separate repos. So we would tend to target, as much as basically saying one app equals one repo, I tend to say one bounded context equals one repo, but you may have multiple processes in that bounded context. But that is just something we've found out works for us more, because otherwise you do end up building multiple repos, which is kind of against the point for one given basically bounded context and one CI boundary. Right. Shared context management, well, dependency manager, not a shared source in repo. So they don't like Go programmers, basically. So those of you that don't know, Go is a 1980s language where copy and paste reuse is king, where effectively we haven't got generics, so we cut and paste, and we don't have package managers, so we cut and paste. So the guys that wrote Go believed heavily in copy and paste reuse. The rest of the world has package managers, for good or ill, like because you can remove things like LPAD and screw one up. But what we're saying essentially is we want you if you have shared code, then you should use your package manager facility to do that. So rather in your organization than saying, okay, well basically just, this repo effectively bolt the code into this repo and then build your application so that, get this subdirectory in. What you want to do effectively is say, if I've got some shared items internally, expose them all by the package manager internally. Get ProGet or something, or just get a file. You can expose basically a folder as a NuGet feed if you want to. So just basically make your package available as NuGet packages. And ultimately, this kind of model leads you down a world of things like everything is NuGet, Octopus, right? Deploy. But yeah. So basically, just use your package manager for your own dependencies internally. And deploy is running instance of the app using the same repo. So the idea, what happens is this. I want to get a clean machine. On that clean machine, only thing I want to basically potentially pre-install is the operating system and a copy of your runtime, right? And then I want to load your app onto that and essentially summon your dependencies, so that I know that this instance only has the dependencies that you need to run and nothing else. I don't want to ship the SDK. I just want to ship your app and its dependencies. Nowadays, you can also use two-stage builds in Docker, which kind of help with this model. Effectively, you load all the SDK that you need to build stuff onto one Docker instance, you build it, and then effectively you copy the built artifact over to another container, right? But you don't want to basically ship all that other stuff. And so you just want to essentially pull everything in apart from do a git clone to get the source code and then pull down the package manager. .NET has a lot going for it in this .NET Core, because essentially you have .NET Restore, and .NET Build now calls .NET Restore automatically. So .NET understands this principle. In places like Python, effectively you have kind of pip freeze, effectively, and pip install requirements.txt, effectively what people do. So effectively you create a text file, and basically with a freeze, then you just install it. Different models, but they're all doing the same thing. Okay. So what I was going to show here, but just I don't have a internet connection to set up, is just I've got a repo for that particular project, and you can go and I can do a git clone basically and pull that project down into a temp directory and then build it, which is kind of the idea. and it would build and then do a restore effectively and pull the packages off the internet and effectively build for you. Just to show you that that whole app is built that way. Basically, I set dependencies, yeah, package manager, right, pip, and yeah, virtual env, yeah, so obviously you may need basically isolation of if you want to install. This is a bit, this doesn't tend to happen so much nowadays. So if I'm installing, say for example, Python onto a Linux machine, I've got a couple of problems. One is generally quite often something like Ubuntu is probably using Python as a result, using something like OpenStack on it, and I don't want to really install my version of Python over the operating system's version of Python. It tends to break things. Second, I might have multiple Python applications running on my machine, so I need to isolate them from each other. So virtual env is a way of saying this Python uses this version of the runtime, these libraries, it's all isolated from each other, right? We don't really have that in the .NET world, but we tend to have basically more of a model of saying, you know, what's in the directory that you're in kind of controls that process for you instead. But avoid things like global assembly cache, right? Global assembly cache means I do not know what version I'm running with effectively. Right. So the mantra is clone, restore, build, and run. Right, that is the gold standard process for a 12-factor app. So git clone, .NET restore, .NET build, .NET run. Right. Okay, so I show that. Config. Store config in the environment. Okay. How many of you store tons of, like, you know, environment-specific variables in web.config files or other config files for .NET, effectively, etc., or ini files in Python land or whatever, right? And how many of you have some slightly overwrought process that takes, I mean, certainly Huddle, you know, the majority of some of the build scripts, they're all written in, you know, Saki and Cake, or they were written in Nant or Rake or whatever was the flavor of the day. Their main job is essentially to say, I go and get these values and I merge them in basically to the config file. They don't actually build anything because MS Build just does that for you, right, or etc. What they mainly do is basically build these configuration files. And it's kind of crazy because we have these overwrought build processes that are just really around template merging. And the other problem is, what am I shipping, right? Really what I want to do is build something and say that is my build artifact. I've tested that on, you know, dev, QA, staging, whatever you call your various environments out to production. Okay? It's immutable. Okay. The same thing that the QA ran against was the same thing effectively that we're about to deploy. The problem with essentially doing all these models of effectively saying I want to basically put configuration in configuration files is that you're not shipping immutable artifacts anymore. You're shipping mutable artifacts to each environment. And that results in every so often you shipping completely the wrong set of configuration values into production. So don't do that. When we talk about configuration, we explicitly mean something that varies between deploys. So you, for example, in .NET, your config file has some things like assembly redirection, etc. And that's really to do with the app needs to run, and that's how it does it. What we mean is stuff that varies between environments, like where is the database located? Where is this other service I depend upon located? What feature flags are turned on, right? Not, I need to assembly redirection. That stuff doesn't vary by environment, right? Your assembly redirection needs to not vary because you are in production or in a dev environment. So, in a 12-factor app, we don't check any of that into the repository. No secrets, no checking in basically our AWS keys into our GitHub repos because people find that pretty fast. So the model for apps you originally came up was, say, store in environment variables. Okay, environment variables are very easy to work with in the sense that, you know, the platform has them. Nearly every language and library has an easy way of saying, go and get me an environment variable value. And they can be configured quite easily in things like Docker or Docker Compose. You saw, do you remember seeing, I can show you if you don't, in the Docker Compose file, there was a section that I was setting environment variables. because my code was then reading the environment variables. And that means that essentially the compose file, which is doing the orchestration, is injecting the values needed in for that particular environment. Okay. Some people, there's some problems with environment variables in terms of really genuinely using them beyond, say, non-production environments. And that's because some folks don't like the fact that basically they can appear as stack traces, so therefore you can see the secrets. And also it can get difficult to manage, right? How do I manage basically rolling out changes to basically, particular secrets, etc., or locations to environment variables? How do I manage rolling out via environment variables where all my X process instances are? So nowadays, a lot more people start to move this stuff over to configuration servers, etcd console, Vault if you want to be particularly secure instead. But take this information out of your application and put it in the environment. Okay. Things like routine table is not considered configuration, right? So anything that basically, one of my rules there would be, would I normally rebuild the application to deploy this? If I would rebuild the application to deploy this, it doesn't count as configuration, even if I might for some reason store it externally. Really separate build and run stages. This is kind of an extension of that. So I build something, and then later, effectively, I take that and put it in an environment. It reads the config for the environment, and it runs. Yeah, this one, you can tell the predecessors are written. They were dealing with a lot of PHP developers who tended to basically just change the production code base. Lovely. Okay. So what I'm going to do is talk a little bit about the ones we talked about, and I'll cover the other three that are not listed. Okay, so at the beginning we talked about what the goals 12-factor apps were. So I'm going to run through those goals again. Hopefully you have a clear understanding of how what I've been talking about now relates to achieving those goals. So use declarative formats, set up automation to minimize time and cost in developers joining the project. Okay. So what I mean by that is effectively, really, what I want to use is, things like Docker or even Ansible or Chef to get stuff running. Okay. Clean contract, maximum portability. Don't depend on things in the operating system, right? Use backing services. Don't depend on the file system being available or a config file being available. Think in terms of how am I going to basically provide that service in a cloud environment or effectively a container environment. Okay. Deployment modern cloud platforms, minimize divergence between development and production, right? So that's just basically this mantra of saying don't wait too long, don't have too many differences in personnel, and don't have too much difference between how I deploy my code in different environments. So things like containers are really useful here because I can essentially say, well, look, I'm going to deploy to exactly a very similar environment or almost the same environment I'm going to run in production. Okay. And we can scale up without significant changes to tooling architecture deployment practices. So all the model we talked about for the design, different processes, etc., effectively, are all about really this elastic scaling that we wanted to achieve. Okay. Oops. Okay. So those are the 12. These are the three I didn't talk about. So you can read those 9. You should have hopefully recognized we were covering them. So the code base, dependencies isolated, that's in other words, use NuGet or something, or pip. Store config in the environment, in other words, basically use environment variables or a config server. Remember that everything we're depending on should not be considered local to the machine which it's running. It should be a backing service that I talk to. Build and run are separate items. Make sure that basically you ship immutable artifacts into run. One or more stateless processes. Be stateless in order to allow us to scale. Use ports. Don't host ourselves in containers. Remember, we're like to basically ship to a model where effectively port binding is smarter. Serverless, containers, etc. Scale out by the process model, right? So essentially, now we've got stateless processes. Just increase the number of them basically and scale out rather than trying to scale up on an individual machine. Fast startup and graceful shutdown. We want to be elastic, so we're going to need to be fast. Okay. Keep development stage in production as similar as possible. This we talked about this a little bit earlier. We're just saying the more difference there is, in other words, the longer the deployment pipeline takes you, the more risk you entail of people not understanding what the production environment is like. The more rapidly you can release changes out through your schedule, the greater you de-risk the difference between your production environment and your development environment. But it also means essentially, they have the same people do it, right? Don't create this pass over the fence divide between essentially staging and production where we say, here you go now, great, we're off to do something else, right? You learn how to run it here and here, use that knowledge in production. Treat logs as event streams. So you'll notice that when I was running Docker, we were getting a stream stuff out to the console. It's just logs. And so if you log to standard out, then what happens in a Docker container is that it gets stored on the host, etc. logs, and you can pick that up with that stuff like FileBeat, etc., and push it across the Kibana. You run that in a container, right? But what you don't want to do essentially is write logs to local disk on the assumption that you can go and retrieve them from local disk. There are two problems with it. One is local disk might not be there. Two, at scale, with lots of processes, lots of microservices, there's an awful number of machines to go and have to track to find something, right? So what you want to do is just push things to standard out and then rely on something effectively taking that stream from standard out and putting it somewhere you can go and then basically investigate it, right? Be that you take it from standard out, you copy it somewhere, and you set an awk on it to you use Kibana on it basically in the elk stack, right? But treat event streams. Quite often, the problem here is if I'm running serverless, for example, Azure Functions or basically AWS Lambda, and if I were to log into basically a file on the local disk, where the hell is that going to be? That container could be gone before I can ever read my logs, right? I have to log to something that's a stream that I can capture and take off that and basically look at later. Yeah. So treat your log as a stream, log to standard out, and then pick up that log and then basically write it somewhere else. And the final one is run admin management tasks as one-off processes. All this is actually talking about is saying, if I have some tooling that relates to my app, include it as the same repo as my app, and basically make sure that it's tested along with my app. Otherwise, what tends to happen is that my tooling, which lives in some separate repo, gets forgotten about. When I want to run that tooling, I realize that it looks basically like the version 4 of basically my app and modifies the way we did things there, but I'm now on version 7 and running this fixed tool is going to be a disaster because we no longer work that way, right? So if I have that kind of tooling, it should live in the same repo as essentially the processes effectively that's supporting. Make sense?
So, if you want to show your appreciation for Ian quickly before we wrap up.